what I'm going to show you is really not very much of my own research at all, and it really emanates from my involvement with the Chesapeake Bay program and a report and a paper that I wrote with about a dozen colleagues from the Science and Technical Advisory Committee, plus a few others outside of the committee, about the potential impacts of climate change on the estuary. So it was a bit of a daunting task because we really tried to go from climate change, its impacts on the watershed, stream flow into the estuary, to the physical impacts on the estuary, changes in the circulation, changes in the chemistry of the estuary, then all the way to living resources. So it's a lot. It involved many fields that I actually don't know, and so it was a great benefit to have the diversity of expertise of the Chesapeake Bay Program Science and Technical Advisory Committee to help out with that. So it's a paper that is several years old now, and I've updated it as best as I can. I still do some of my own research on Chesapeake Bay and climate change. I'm particularly interested in how circulation changes in the estuary with changing climate, and I'm currently involved with a few projects involving the estuary. So, as you know, the bay is a very heavily degraded estuary, and in the short time I have, I won't be covering all of the dimensions of how climate change can influence the estuary, but I picked three metrics that are really key for understanding the health of the bay. And I thought I'd just talk about what we might think, and really in a kind of a qualitative way, because we don't really have rigorous information, projections about impacts on these three metrics here with probability distributions and all of that. We're just not at that level, but I think we are at the state where we can draw general conclusions that can be helpful in restoration. So those three metrics are, and these are like centerpieces for restoration, are the amount of oxygen that is in the bay. That affects numerous biogeochemical and ecological processes and functioning. Submerged aquatic vegetation, which of course is an important habitat for a variety of fauna and plays its own role in maintaining a sediment, a surface sediment that has some integrity. And then finally oysters, which are important filters in the bay and a keystone species in the bay. And there have been really quite spectacular changes, declines, negative changes in all of these metrics here. And the Chesapeake Bay program, the partners involved in the Chesapeake Bay program are attempting to restore or at least improve the bay's health as measured by these metrics. So I'm going to talk about, how climate change might challenge or potentially assist in the restoration around these three metrics. So we talk about climate change in estuaries. It's interesting because the estuary really lies at this point where the atmosphere, the ocean, and the land meet, right? It's like a line, a point where they all meet. And what that means is that the estuary can be affected by climate change in a multitude of ways. It is certainly heavily influenced by what occurs in the watershed, in the Chesapeake watershed, and that affects the quality and quantity of runoff into the bay. And certainly interaction with the atmosphere, changing wind patterns, changing radiation field associated with increased greenhouse gases, will affect the physical aspects of the bay and also the chemical aspects of the bay as CO2 invades into the estuary. And then, of course, on the open ocean side, one of the prominent ways in which the estuary is affected is as a result of sea level rise and what is in the quality of the ocean water. So it becomes a challenging problem to try to understand all of these impacts. So what do we know about how Chesapeake Bay is changing? Well, we have the benefit, since it's a very well-monitored estuary, we know that the bay is warming, and it's pretty much following the regional air temperature patterns, which in turn are largely due to, it's an anthropogenic effect. Much of the warming that we're seeing in the Northeast is a result of increased greenhouse gases. We also know very well that sea level is rising in the Chesapeake, and this is due to thermal expansion of seawater. It's due to melting of glaciers. It's also due to some subsidence in the region that has been going on for a long time as a result of isostatic adjustment, post-glacial rebound effects. So when we look to the future, we want to understand how these trends will change into the future, and we have to rely on climate models to give us a view of how the climate of the region will change. And what we put into those climate models are emissions of carbon dioxide and other greenhouse gases, different scenarios that we might envision for the future. And this actually is not the most up-to-date list of scenarios, but it's a set that is commonly used. So you see annual CO2 emissions on the vertical axis and time throughout this century on the horizontal axis, and a variety of scenarios that are really storylines about how global society and technology will evolve. And often sort of a high range, high emission scenario and a low emission scenario are used for illustrative purposes, but there's really nothing special about these scenarios. We could certainly go higher than the highest on this, and we can go lower than the lowest on this. And to illustrate that, you can see that right now we're actually moving along the upper end of that trajectory. And yet, what we hope really to avoid the worst climate change is to reduce those emissions, way below the lowest scenario that's there to 20% of current emissions by 2050, and that avoids the sort of 2-degree threshold that's often given as a dangerous threshold for climate change. So what you get from climate models is projected change in regional air temperature, and by inference, change in the temperature of the bay. And that means that effectively, this shows the summertime conditions. Under a high emission scenario by 2100, summertime conditions in terms of temperature in the Chesapeake would be like that of a Florida estuary. So that's a really big change. What you do notice here also is that in the short term, the emission scenario doesn't really matter that much. There's enough inertia already in the climate system, and CO2 has a long enough lifetime that we're going to have some climate change really no matter what, even if we dramatically reduce emissions. Of course, we already have the climate change, so maybe that's an obvious conclusion. All right, so I don't have time to show projections for all the variables, but when you look at what climate models say, we know some things quite well. We can say with a lot of confidence that CO2 will continue to rise, sea levels will continue to rise. It's very likely that the bay will continue to get warmer, and also what climate models show a lot of consensus about is that the wintertime precipitation, winter and spring precipitation will increase. Still likely, but with somewhat less certainty, we can say that the precipitation will become more intense. That is, when it rains, it'll rain over maybe a shorter period of time, but as hard. That will cause stream flow to be flashier. And as a result of the higher winter and spring precipitation and more snow melt, we would get increased winter stream flow. And then finally, another fairly consistent projection of climate models is that extratropical cyclones, nor'easter-type storms, will increase in the future. Now, whether that happens in the Mid-Atlantic region or not is not really clear. So that's why there's somewhat less certainty there. So one of the challenges that the estuary is facing is eutrophication, excess nitrogen that's causing algal blooms, such as this coccodinium bloom shown here, which is also a toxic algae. One of the consequences of those blooms is that when they settle to the bottom, oxygen is consumed, and that increases a region of low oxygen waters. That's what's shown in this figure here. Shows the summer hypoxic volume in the bay has gone up quite dramatically, as has the nitrogen loading in the bay, which is presumably due to that, which is presumably causing that increased hypoxia. So what the future might bode is when we have higher spring stream flows, what we've seen in the past is that leads to more stratification in the bay. It kind of revs up the biogeochemistry in the bay, more photosynthesis, more respiration. That leads to declines in bottom water oxygen. Higher temperature will also increase the biogeochemical cycling of the bay, ultimately increasing the rates of respiration and declining bottom water oxygen concentrations. The higher temperatures will also decrease the solubility, just a purely physical chemical effect, and we'll have less oxygen in the bay. So many factors are pointing towards climate change exacerbating low oxygen conditions in the bay, therefore making it a challenge for bay respiration. Then finally, there's some evidence also that higher CO2 increases heterotrophy in the bay, which would increase respiration. So there's really a lot of factors pointing in that direction. So I'll now move on to the second metric, submerged aquatic vegetation. Of course, it's a very important habitat, and as I noted earlier, it's important for the integrity of the seabed as well. What we've seen from observations is that when we have hot summers, the eelgrass in the bay tends to die back, and that's because it's currently at its southern limit. So it's at an extreme point now. So when we have hot summers, we see diebacks. So we can expect under continued warming that we would get less eelgrass in the bay. Now the higher spring flows that we also expect tend to increase algal blooms and decrease water clarity. I mean, this has been one of the problems with submerged vegetation in the bay, is that the light's basically being blocked out by the plankton. So that will lead to a SAV decrease. And as I pointed out, the higher temperature will also push you in that direction. And SAV can also respond to low bottom water oxygen in a negative way. So again, many things pushing towards challenging the restoration effort for SAV. One possibly positive thing is that SAV do respond, CO2 is food for plants, and they will respond positively to an increase in CO2. So that may help out and make the SAV somewhat more resilient. Now I'll go to my last metric, oysters. And oysters, of course, they've been over-harvested, but they've also suffered from disease. Two diseases have helped to decimate the oysters throughout the Mid-Atlantic region. And this nice work that's been done in the Rutgers Haskin Shellfish Lab showing that the propagation of oyster disease is directly related to the warming of winter temperatures. And that's allowed basically the disease to overwinter more successfully and be that much more harmful to the oysters. So that will challenge restoration efforts, continued winter warming. And then on top of this, we have acidification, and this is more recent research showing that higher CO2, of course, makes the water more acidic and makes oysters less able to calcify. So we can expect some negative impacts there as well. So the bottom line is that climate change it will significantly impact the bay and present additional challenges to bay restoration and fisheries management. So what do we recommend? Well, we're already seeing climate change. We're going to continue to see climate change. So we need to adapt. to that. That means we really need to actively account for climate change and restoration efforts. It really needs to be integral to the efforts. Long term, it's a very challenging problem because climate change comes from everywhere in the world. Every CO2 molecule, no matter if it's emitted in Australia or New York City, contributes to global warming. It's unlike the eutrophication problem, which to some extent can be locally controlled. But really, we need to reduce emissions. It makes it difficult because we're just one little watershed in the globe. But if we join together, right, and we make a statement that ecosystems are being threatened, and among them Chesapeake, and make it an example that we'll reap benefits if we reduce emissions, then we should do so. So that's a more difficult problem, but I think equally important. And sometimes we forget this. We've had very spectacular successes in environmental restoration. We're always focused on the problem, and we forget, it's kind of like having a to-do list. We always put our to-do list, but we very rarely write the what have we done list. And this is a what have we done list, a spectacular success. The amount of acidity we're getting in rainwater now has dropped dramatically over the past 20 years as a result of the Clean Air Act. And of course, there was a lot of pushback against this too, but we really had our cake and ate it too. This happened while heat and electricity generation went up in the U.S. Costs basically remained flat if they hadn't gone down, and and we were able to reduce the acid-causing emissions of sulfur dioxide and nitrogen oxide. So, I hope it's a depressing talk in a way because climate change will definitely challenge estuarine restoration. I think it'll make it more difficult in most cases. There could be some positive benefits. I pointed out one of them, but largely it's going to make things more difficult. But I hope that you recognize that if we have good science, we have good policy, we can solve environmental problems. And with that, I thank you very much.